Hello. In this video, we are going to talk about taking a double integral that may be in Cartesian or rectangular coordinates, so across some rectangular region, or a region basically defined as x's and y's, and converting them into polar coordinates. So I've used G here to just say it's a different type of region, but really R, G, D, whatever you want to call that region. Variable is a variable as long as you know what it means. So thinking about this as a function in terms of polar, R cosine theta representing X, R sine theta representing Y, and then integrating dr d theta. We want to make sure that we notice that whenever we are converting to polar coordinates, we're going to need to add that extra integrating factor here, this r. So let's look at an example. So we're going to evaluate the double integral across some xy region, e to the x squared plus y squared. So integrating first with respect to y and then x. But if we look at this, and we tried to integrate this with respect to y, that'd be pretty confusing for us. So some things we want to notice is, we see a polar property here, x squared plus y squared is r squared. And we think, okay, well, maybe we can convert this into polar coordinates. So let's look at what R is. And R is a semicircular region. And pretty much when you're thinking about anything being mildly circular, or you read that word circle or you see a circle in your region, you might want to think about converting to polar coordinates. So R is a semicircular region bounded by both the x-axis and y equals the square root of 1 minus x squared. So let's think about or consider graphing our region. What does y equal the square root of 1 minus x squared look like? And that is a circle. That's, if we tried to manipulate this, we could rearrange this and have this look like a circle of radius 1. Because this is positive, it's that top half of a radius 1 circle. So my region, since we're also bounded by the x-axis, my region is this semicircle. All right, so let's think about redefining our bounds here. Well, my radius extending out, no matter how I extend out, my radius is going to equal 1. And then my degree measure, theta, is going to start at 0, and we're going to rotate all the way around to where theta equals pi. And then, of course, as we mentioned, this x squared plus y squared is equal to r squared. So let's think about what that looks like when we set this up in terms of polar. We're going to set that first integral. Theta goes from 0 to pi. My second integral, we have r goes from 0 to 1. And so my function, which I'm integrating, e, that's going to become to the r squared power. X squared plus y squared equals r squared. So now we want to make sure that we include our additional integrating factor r, and then we integrate dr d theta. So this is pretty easy for us to integrate with a quick u substitution, but what I want you to make sure you understand right now is how I set this up, how I converted from my rectangular equation to my polar equation or integral. So pause, make sure that makes sense to you. Now let's evaluate this. So I've got 0 to pi. If I'm going to do my u substitution, I'm going to say, well, let u equal r squared. That means du dr is 2r, or rather 1/2 du is r dr. So I see that r dr. I can turn this into u. I'm going to go ahead and make sure that I change my bounds as well. So u equals 0 squared is still 0. U equals 1 squared is still 1. So I performed a calculation to turn these r's into u's. It just so happens that they remain the same. So I've got the integral from 0 to 1 of e to the u times 1/2 du d theta. So now if we look at integrating this, I'm going to pull my 1/2 out in front. I'll still have my integral from 0 to pi, and those are in terms of theta. And then integrating e to the u du is just e to the u. So I have e to the u, and I need to evaluate that from 1 to 0 before I can perform or determine my second integral. So that is 1/2 the integral from 0 to pi of e to the 1 minus e to the 0 d theta. E to the 0 is 1, e to the 1 is just e. 1/2 the integral from 0 to pi of e minus 1 d theta. And each of these can be very quickly integrated, considering that that is a constant. We really don't even have to treat it as two terms. We have 1/2 e minus 1 times theta from pi to 0. Plug in pi, you're going to get e minus 1 times pi. You plug in 0, that's going to 0 out. So my answer is 1/2 e minus 1 times pi. All done. Email me if you have any questions.